Now we have proved a lemma for domain omega of this form. It is bounded by two curves. These two curves are graph of a function which y as dependent variable and x as independent variable. But we also has a domain of other form. That is, the domain is bounded by two functions where y is independent variable. Okay, for that case, that is if omega, for omega of this form, xy, y is bounded b minus b plus, and x belongs to c minus y to c plus y. For the other type of domain, omega, we have similar result. So for this domain, if q is continuous over the closure of omega, that is omega as the union of omega and its boundary, and the partial derivative exists and bounded over omega and continuous, then we have similar result. Equal q dy. Okay, the proof is the same as our lemma. Okay. Now combine these two lemma together, we have the following important theorem. That is the Green theorem. So suppose omega has both forms. These two forms may be called 1 and 2. 1 is the form given here. This is 1. That is omega bounded by the graph of two functions. These two functions, x is independent variable, or omega can also be expressed in this form. That is, it also bounded by the graph of two functions, but now y is the independent variable. So this is the second type. So we assume that omega has both of these two forms. Okay, and the p and q are functions defined over the closure of omega, continuous, and bounded, and has bounded derivative. First order derivative. Then our result is that here the orientation of the boundary is the positive orientation we just introduced. That is, when you go along the boundary of omega, omega is on your left side. Okay. So this theorem, the proof of this theorem is quite simple. Just add the previous two results. So but we still want to state it here. Since omega is of the first type, we have we have a minus sign. We will take a minus sign to the double integral. And since omega is of type 2, we also have Now adding these two equality, we obtain our result. So the proof is quite simple. Okay. So which kind of omega has this form? Both type 1 and type 2. So for example, this omega, you can consider it as the graph of, you can consider this as the graph of phi plus x, and the lower boundary as a graph of phi minus x. So from this, you see that omega, our omega here is of type 1. But you can also consider this omega as type 2, because this, you can consider the boundary consists of the left part, that is the graph of y equal to psi minus, x equal to psi minus y, and the right boundary, the right part is x equal to psi plus y. So our omega here is of both type. It is of type 1 and of type 2. Okay, but even if omega is not has these two type, two sub simultaneously, maybe, but we can divide the omega into several pieces. Each piece has both form. Okay, for example, if omega is given in this way, then it is not, no, maybe we, okay. If omega is of this form, so it cannot be, it is not of type 1 and not of type 2, as you can see. It could not be a function, a domain to be type 1. If a domain is of type 1, any line parallel to the y-axis could have at most 2 intersections with the boundary of omega. Okay, and if a domain is of type 2, then any line parallel to the x-axis can also have at most 2 intersections with the boundary of omega. But in our omega, in this picture here, for this omega, we have a line parallel to the coordinate axis has more than 2 intersections which the boundary of omega. So this omega is neither of type 1 or 2. But we can, for such omega, we can still apply the Green formula. Why? Because we can divide this omega into several pieces. Each pieces is of both form. Each piece is of type 1 and also of type 2. For example, for this omega, we can divide this omega using some curve. Okay, then each pieces, for example, this pieces, you can see that it is of type 1 and 2. But so adding the double integral over the whole omega equals the double integral over every pieces. But the boundary of every pieces is more than the boundary of omega. The boundary, for example, the boundary of this piece, consists of part of the boundary of omega, that is this red part. It also has this part. You need to also contain the curve inside the domain omega. That is, I draw in blue. Okay, so this will affect the line integral in the right hand side of the formula. But fortunately, when you consider this piece, when you consider this piece of omega. You also applying the Golin formula in this piece. You will also the double integral over this piece. We also we also produce line integral over the same curve as the part of the boundary of this region, and which the opposed direction orientation. You have one piece here, and you along the same curve you also have an integral which is reverse orientation. Therefore, the two terms cancel. So this means although you need to add some curve to divide the omega into several pieces of good domain, but the curve you add, the line integral over the curve you added cancel. Therefore, they will not appear in the final result. So the Golin formula remains true even for domain of this type. Okay. Now this is the Golin formula. Now as application, we consider a simple example. Omega is a region which is smooth boundary. Boundary is smooth, and 0 is a point in omega. Now we compute this integral. So this is an open domain omega. 0 is here inside omega. So we want to compute this integral, of course, without indicating along the positive orientation. So in this case, our P is y over x squared plus y squared, and the Q is minus x squared plus y squared. Okay, and the problem is that this P and Q are not continuous at the origin. P and Q are not continuous at the point here. So you cannot apply the Golin formula to this problem. And moreover, because 0 is a point in the boundary, 0 is a point in omega, and we are integrating along the boundary of omega. So for any xy on the boundary, P and Q are continuous. The two functions P and Q not continuous at the origin, but the origin is not a point on the boundary. So these two functions are continuous at every point on the boundary. So this line integral makes sense. So even since it makes sense, we should be able to compute the value. But because the omega is given arbitrarily, it's not explicitly stated what omega is. So the boundary curve, the omega, is also not explicitly given. So we could not compute this line integral using our famous well-known formula. And moreover, it seems that this integral should depend on the curve, that is on the boundary of omega. Equivalently, the integral of this should depend on the domain omega. You take different omega, usually this the boundary curve is also different, so the result will change. Usually this is the case. But for this problem, as we will see, the result does not depend on the sharp on the omega. Does not depend on omega. So the trick is to use Golin formula. So the left computation tells us that the partial derivative of Q with respect to x and the P with respect to y by the left computation, you will see that the result is 0. Okay, This is the first step. But to apply the Green formula, since this P and Q is singular at origin, we need to remove a small disk from the origin, radius epsilon. Let be epsilon 0 contained in omega. We apply Green in this domain. That is, we apply Green theorem in this domain, the subtle domain. Okay. Then by Green formula, we see that the integral what we want to compute, p dx plus q dy. So the boundary of the subtle domain consists of two parts. The first part is the original boundary of omega, but since we remove the a neighborhood of the origin, we will obtain another boundary, that is the circle around the origin. And the orientation of the circle is clockwise, because the orientation must be positive oriented with respect to omega. Therefore, when you go around the curve, you need to ensure that omega is on your left side. So it should be oriented in this way. So, but we also consider another orientation. That is also counterclockwise. So if you oriented the circle anti-clockwise, you need to add a negative sign. Okay. So we want this to be the boundary of this domain, p dx plus q dy. The boundary of this consists of two parts, omega boundary and the circle. But it should be a positive sign here. Here usually should be a positive sign, but because we use the negative orientation on this part, so we taking negative orientation, you will have a negative sign. So the positive sign should not. We should use negative sign. Okay, we should use negative sign here. This is why we take a negative sign. Now, by Green formula in this domain, we can apply the Green formula. By Green formula, this is omega removing the circle qx minus py dx dy. By our computation, this is 0. Okay, so from this we see that the integral we want to compute equal the integral around the circle of radius epsilon, which anti-clockwise orientation. For this circle oriented anti-clockwise, it is negative to omega. But this is what we need, and so we see that the integral over omega anti-clockwise equal the integral over the circle anti-clockwise. So the circle is very simple curve, and we know the parametrization, x equal to cosine epsilon cosine t, y equal epsilon sine t. Therefore, we can use the orientation to compute this integral. Okay, then using this result, our omega integral, our integral over the boundary of omega should equal the integral over this circle, and this can be explicitly computed. Okay, I will not do this computation in detail.